Okay, the second major mechanism is an increase in hemoglobin concentration. And hemoglobin increases as a response to hypoxia. Now, unlike hyperventilation that starts immediately and takes about 3 days to peak, the increase in hemoglobin starts slowly and takes about 6 weeks to peak. And a typical value for hemoglobin, if you spend enough time at around 5,000 meters plus, is somewhere between 70 and 20 grams per deciliter. And once you return to sea level, your normal hemoglobin levels are restored relatively quickly, again in just about 6 weeks. So, what causes your hemoglobin to rise? Fundamentally, it's a response to hypoxia. Hypoxia stimulates the production of erythropoietin, EPO as it's often known, and EPO basically stimulates the production of red blood cells. So over about a 6-week period, there's a slow but steady production in red cell mass. Now the trouble is, there's both advantages and disadvantages to this. Because if we increase our hemoglobin, then basically our blood is effectively becoming thicker and more sludgy because it has more cells in it. So there's an increase in blood viscosity, and that also increases the workload on the heart. That also increases the possibility of intravascular thrombosis. And so once you get to about 18 grams per deciliter, you're in that kind of precarious halfway house where you're getting potential benefits of more hemoglobin to carry more oxygen to the tissues, but a high level of viscosity, an increased workload on the heart, and the risk that the blood will sludge and thrombose, effectively leading to a venothromboembolism. Now, no one knows exactly what the ideal hemoglobin is in this balance, but most people accept it's around 18 grams, and once you get beyond 18 grams per deciliter, and the disadvantages start to outweigh the advantages. And there is a condition called chronic mountain sickness, or Monge's disease, where typically hemoglobin levels are around 22 or more. This is a particularly serious condition. You see a lot of it in the Andes amongst people that live there permanently. I'm not going to talk about it in any more depth or detail in this particular talk. Another thing that happens is capillary volume density increases as a response to sort of hypoxia. And what that does is it decreases the distance between the blood and the mitochondria. And so in theory, might facilitate the transfer of oxygen from the capillary through the cellular layers into the mitochondria itself, where it obviously can be utilized. There is a genetic basis to acclimatization as well. We know that some people are more predisposed than others to altitude illness, and we know there are some people who are kind of super climbers. There is some evidence of familial clustering, and we know that there's a resistance to hypoxia in high altitude residents, and there's genetic selection, of course, in high altitude populations. We know that there are genes associated with the development of high altitude illness, and all of that points to the fact that genetics probably play an extremely important part in determining whether you can or can't acclimatize to altitude. So if you go to climb Kili and you don't make it, it may be that your parents are more responsible for the genes they gave you than any other extrinsic factors. And there are at least 58 candidate gene pairs that are currently being investigated that might play a role here. Again, I don't think you need to know this in any great depth. It's certainly interesting if it's something that you want to go and do some further reading about. Okay, so here we are. This is another one of the beautiful campsites on the slopes of Kilimanjaro. And you can see that we're above the cloud cover here at around the 4,000 meter mark. And in fact, Mount Meru, the 4,000 meter peak that I talked to you about earlier, which is one that people sometimes use as an acclimatization climb before attempting Kili, is actually just below there.